Well, good afternoon. I'd like to thank the sponsors for the very kind invitation where I get to talk about my favorite topic, space research. So I am Delores Knipp. My graduate students and I work on Air Force space-sponsored research in the Aerospace Engineering Sciences Department at the University of Colorado Boulder. You might guess from the name that we are working on the edge of basic and applied sciences. And the project with the primary question, how does heating beget cooling in the upper atmosphere, which might seem like kind of an odd question, originally was an applied project. But sometimes the way things go, you don't know when you get into a research project if you're actually going to be going forward into applications or maybe taking a step back and saying, is there a fundamental problem here that I'm not understanding? And that is what has happened. So I am going to try to give you the story of how we came up with this particular question, and probably just importantly, why do we care about answering a question like that? The why we care part of this comes from the fact that we live in space. We live beneath space as far as we're concerned. We live in a very sheltered environment beneath Earth's atmosphere, within Earth's magnetic protective covering called the magnetosphere. But nonetheless, even living beneath that, we are a spacefaring nation, and our space assets, some of our humans, and many of the signals that we rely on for communication all either are in that environment, the space environment, or they transit the space environment. So many times we need to be thinking, and actually all the time as far as Space Command is concerned, we need to be thinking about what is going on in that space environment and what are the dynamics. So I wanted to give you a primer on what is going on in our upper atmosphere. We live in the part of the atmosphere, or we're operating in the part of the atmosphere called the upper atmosphere that responds very dynamically to energy input from the sun. It expands when energy comes in, it contracts when energy goes out. The reason that we care about that is in low Earth orbit, where most of our space assets are, Space Command actually tracks tens of thousands of objects that are thumbnail size or larger, traveling at 7 to 10 kilometers per second, which if you think about that, that is really fast if you run into it. So Space Command, in addition to tracking these things, has a job of making sure that collisions don't occur, at least to the best of its ability. So there's a lot of orbit calculations going on. One of the things that we know about each of these orbits in low Earth environment is that they are perturbed by any changes in the Earth's atmosphere, expansion and contraction. We also know that the beautiful things that, if you've ever had an opportunity to see it, called the aurora, mostly at high latitudes, that aurora and the associated phenomena are really representative of energy coming into the atmosphere. The energy comes in at high latitudes, but it doesn't stay there. It propagates out in waves. And there has to be, in order to maintain energy balance, other means of getting the energy out. One of the things that we learned as we were trying to understand some of Space Command's problems with forecasting these orbits or changes in orbits is that there is sometimes really unexplained dynamics. And Space Command came to me one day and said, we have a problem with our forecasts. And I go, well, what is your problem? And they go, we don't know, you're a researcher, you should be able to figure that out. That led my students and I on a 3-year trek to understand how the atmosphere is cooling. So let me give you a little bit more of this story and tell you that the sun in general is a pretty benign, middle-aged, well-behaved star. But sometimes it has fits, and it produces incredible eruptions that you get to see sometimes on a site called spaceweather.com, or sometimes even mentioned by your various local newscasters. These things that are eruptions from the sun sometimes show up as photons, and sometimes show up as huge ejections of mass, maybe even more than a battleship being sent out, moving out into space at supersonic speeds. We have some basic ability to forecast these. We generally know when these things are coming towards Earth, and we're able to say, well, they're going to create an auroral display or not. To the military, we would say an expansion of the atmosphere or not, and further orbit perturbations. NASA would give us a nice artist's rendition and say, before the storm, we would have a nice round upper atmosphere, kind of trails off into space. During such a storm, the atmosphere expands and then it contracts back. And that's all a kind of an orderly process that we know something about. And it looks to a satellite that might be at a fixed altitude in space, like the density has some background level. Then 6 to 8 hours after a storm starts, after one of these eruptions reaches Earth after about 3 days, we get an expansion of the atmosphere, and then over the course of 12 to 24 hours, it kind of cools back to normal. The cooling we've always understood to be produced by a gas, which we call we refer to as a greenhouse gas, but it's carbon dioxide. So the background cooling is generally done by carbon dioxide, high in the upper atmosphere. And so the reason that that's important is satellite orbits can change very markedly during the course of a storm, but we can forecast that to a high degree of accuracy, except when we can't. So what goes wrong there? We realized in the course of answering Space Command's question that some storms do go rogue, and we didn't know why. Why could there be fast heating and then suddenly equally fast, if not faster, cooling? How could such a thing happen? And furthermore, what would it do to satellite orbits? So rather than the picture that I showed you before with a nice slow decay in density, we actually see the atmosphere shudder and contract. What could cause such a thing? After much thinking and getting our hands on data that are now being measured by NASA, one of the things that we realized is that during storm time, it's not only carbon dioxide, but also there is the creation of a type of gas. It's a trace constituent called nitric oxide. It's an interesting molecule because it's not quite balanced. One side's heavier than the other, and that means when it gets excited, it twists and vibrates. And if you know much at all about spectroscopy, you would say, that's an opportunity for that molecule to radiate in the infrared. If you remember the discussion this morning about the hand glowing in the thermal portion of the spectrum, our atmosphere during storm time actually turns into a big glowing ball, and that is how it gets rid of excess storm energy. During these rogue storms, what we found out from the NASA measurements and now can confirm by DoD measurements is that the system produces an unusual amount of nitric oxide, and the cooling goes crazy. The atmosphere cools, it overreacts, and practically collapses. Now, it's not like the whole thing is going to sit down and just on top of us, but the upper atmosphere that is very tenuous does in fact contract. what would cause such a thing? Why would we have storms like that go rogue? Well, that was the really basic part of the research. What we found out, just recently published, is that for the fastest storms that actually create shock waves on their way to Earth, so they create supersonic shocks that approach Earth's atmosphere, these shocks create extremely intense aurora, intense currents that flow through the upper atmosphere, and those aurora actually create nitric oxide. So the aurora that's actually putting energy in is creating a chemical that helps nature rein itself in so that we don't lose the edges of our upper atmosphere. The result is very intense cooling, and immediately thereafter, very intense heating rather, and then immediately thereafter, very intense cooling, sometimes overcooling. That is not in any of our operational models at the moment. That is something that as we further develop the understanding, we have to convince the modelers who are supporting DoD that we really have to have that aspect into our system. So just one graphic to show you before I close what this looks like. My students decided that since we don't see this on a global view, our satellites look at it kind of piece by piece, we would create a composite. And so for the middle part of the storm population, we looked at latitude and time. And we looked over the course of about 8 days, and you can see at high latitudes where the aurora normally are, we do have the nitric oxide glowing. And then storm time comes along, and here the glow now extends all the way to low latitudes. This should say 25%. So the most intense storms, we have the Earth glowing at all latitudes for extended intervals of time. This is the key piece that we needed, bringing NASA and DoD data together to understand that we need to put this aspect in to do our forecasting. So to summarize, how do heating and cooling in the upper atmosphere affect satellite drag, and why do we care? We do know that we have rogue eruptions from the sun, those that come very, very fast, and they influence our upper atmosphere, changing the cycle of heating and cooling, and changing the way that low Earth orbiting satellites orbit. Tracking and controlling these satellites is a significant challenge, not only to DoD, but to civilian agencies worldwide. So what I hope to convey to you is that we have merged both the basic and applied sciences to understand that investment in the monitoring, simulating, and understanding Earth's far out upper atmosphere is an important part of what we do to contribute to the safety of our population, and to those who actually rely on communications and satellite technologies worldwide. Thank you.